We've done a lot of integration. You have a lot of rules. But the thing that we have used the most to integrate at this point is a form of U substitution. But sometimes we're going to be dealing with products that have a mixture of algebraic and trig and transcendental functions, and we're going to have to use a much more advanced integration technique called integration by parts. So the integration by parts is used to deal with a product that U sub can't integrate. So we have dealt with U substitution with some product situations. So a product that U sub can't integrate. So you have dealt with products up to this point, but you've only been able to use U substitution. So some examples of these that we're going to have to use integration by parts for would be a mixture of algebraic and transcendental, or maybe algebraic and trig. This is a product, but this is not something that is integratable by just using U substitution. Same thing with x, ln of x. So let me show you where the rule comes from. The first thing that you need to know is, of course, there was a product rule for differentiation. So what was that rule? And we're going to use U and V for this rule. I need to be really comfortable with that. So if we're multiplying U times V, it would have been the first, right, times the derivative of the second. And the derivative of V would be dv dx, because everything, according to this, is with respect to x. So I'm paying attention to that variable. Plus the second, which is V, times the derivative of the first, which is du dx. So ultimately, there's an algebraic manipulation. So what we're going to do is we're going to take the integral of both sides. So if I integrate this side and I integrate this side, so let me show you kind of what that looks like. The integral here would just be uv, and then I would have the integral of u dv dx, and then that dx is part of the integration. We are integrating with respect to x, correct? And then plus the integral of v du dx times dx. Again, the integral with respect to x. And those dx's do reduce. They're representative of the same thing, so the same unit of measure. And what we're left with here would be the integral of u dv plus the integral of v du. So what I have is uv is equal to the integral of u dv plus the integral of v du. The idea here is that you are given this piece. You are given that you are trying to integrate u dv. So we would look at this as u and dv, u and dv, u and dv. So if you're given this, then you're going to have to manipulate to move this side, move this piece over, right? So we're going to have to move some stuff on each side of the equal sign in order to get my formula. So the formula is the integral of u dv is equal to uv minus the integral of v du. Now that's a hard formula to remember. There's too many things that look way too similar to each other. So you're going to hear me say this a lot. Sudov, uv, svada. Now that sounds like gibberish. But that's what this piece, it helps me remember what this formula is, right? The s takes the place of the integral. So this is sudov, uv, svada. Sudov, uv, svada. Now you do have to remember that there is subtraction there. That's a big takeaway. But sudov, uv, svada will help you remember the formula. So go ahead and write the formula. Sudov equals uv minus svada. That way you have that marked off. You had that in that correct spot on your notes. Formula for integration by parts. Now, the biggest challenge is going to be choosing which part to assign as u and dv. And there's some different strategies for this, but this is going to be the biggest trick. And we're going to do several examples that's going to help you make sense of this. But to do this correctly, the integral, well, it's not going to simplify into anything nicer, right, if you do it incorrectly. So once you figure out some of the nuances and some of the way this strategy works, it's pretty simple. But sometimes you can start down a path and realize that you're wasting quite a bit of time. So there's a nifty little rule that we use to help us define u. So this is the The word that we use to describe this is lyate. Okay, we use lyate. So it's not 100% guaranteed to work all the time, but it's going to work for everything you do in this class. So this is to remind you how to define U. Okay, so this is going to basically tell us how to define U. And lyate, we're going to say this is logarithmic. So we're always going to pick the U. If there's a logarithm, we're going to pick that for U. If there's not a logarithm, then we're going to use inverse trig. If there's not a logarithm or an inverse trig, then we're going to look for the algebraic piece. And if there's not an algebraic piece, then we're going to look for the trig piece. And then this is the exponential. So lyate is the word that we use to help us remember the order of defining U. Okay, and again, it's not 100% guaranteed all the time, but it is going to work for everything in this class. So let me do an example so it'll make a little bit more sense as to how we pick these things. So the first thing I'm looking at here is I've got an x times a sine of x dx. I cannot use u sub here. Okay, they've got trig and algebra mixed together, and this does not take into account that piece, so I can't use regular u sub. So my job is now to define u and dv. Remember, that's my formula. My formula is sud of, right? So the u, dv are the things that I am given. And if lyate is the word that I'm going to use here, algebra comes before trig. So I'm going to use the algebraic piece as my u. So if I define u as x, that means that this sine of x dx is going to be dv. Now, just like we did with u substitution, we still have to find du here, and we still have to go backwards and go from dv to v. Your derivative and your integral rules are all mixed up on this thing. So you have to be really confident and really comfortable going both directions. So if I'm going to take the derivative of x, it's just going to be dx. Remember, this is a differential derivative, same way I always have done u substitution. I am now taking the integral of sine x. So think about your trig circle of happiness, and this is going to be negative cosine of x. Once you get that, you are now going to plug it into your formula. So your formula here is sud of uv sfada. So I'm going to just draw a little arrow just to kind of get me around this. So equals. So this is my sud of uv, right there. X times negative cosine of x. Now, I'm going to make sure that I write this as multiplication. So I'm going to do negative x cosine of x. If I put the negative in the middle, it might look like subtraction. So this is my uv. And then I have subtraction here, minus sfada, v du. So I'm going to have negative cosine of x dx. So this is a negative still. Now, if I can see that in advance, then I might be able to go ahead and do minus a negative. That would be fine. You could go ahead and convert that to positive if you wanted. But if you can't see it in advance, then we can go ahead and change it at this step. Now, the integral of cosine, again, trig circle of happiness, is going to be sine. So you get negative x cosine of x plus sine of x. Did I say negative? I didn't mean negative. So trig circle of happiness, go backwards, right? Plus c. That is the integral of this. Now remember, what you're finding is if you took the derivative of this, you should get that. And for this question, I'm going to go ahead and check that. I'm going to go ahead and make sure that I feel confident with that. So we're going to say, let's go, if that was f of x, I would call this f prime of x. So let's go the first times the derivative of cosine. The derivative of cosine is negative sine. Plus the second, which is sine of x. Oh, nope, sorry, cosine of x. Looked at the wrong thing. Plus the second cosine of x times the derivative of x, which is negative 1. And then the derivative of sine is just cosine. Now, obviously, the derivative of c that's a constant, right? So that's 0. So let's see here. Does anything simplify? It should. It better. So x sine of x, then minus cosine of x, then plus cosine of x. Oh, yep. Sure thing. When I take the derivative of this function, I get x sine of x, which is exactly what I wanted. So we're not going to check all of them, but I did want to show you the check that this is part of why this process works. Now, I do want to take just a second, and I'm going to draw a little line here, to show you what would happen if you picked the wrong u. So if you picked, so if you went through the process and you said, well, let's just make u sine of x, and let's make dv x. Let's switch those and see what happens. Okay, no problem. Let's try it. That means du, that's the derivative of sine. The derivative of sine is cosine. And then if I integrate dv, I'm going to get 1/2 x squared dx. So now if I set up my set of uv, my uv is now 1/2 x squared sine of x minus, and then I'm going to have the sveta, right? So v du, and then I'm going to have 1/2 x squared cosine of x dx. I think I wrote ds right there, and I'm not quite sure why. So this is supposed to be dx. I know I'm squeezing all this in really tight, but you'll notice this right here, that would be another integration by parts. This is just going to continue the cycle. It's just going to keep going and going and going, and you're never going to get to an answer. So if your cycle doesn't end ever, then you're like you've picked the wrong thing, right? This is spinning wheels is what this is, and you're never going to get anywhere with it. So it's important that you can pick the u correctly by using this Lie8, by using that that word.